Good afternoon, everyone. My name is Zhang, and I'm going to present our research work exploiting backdoors of naturally trained deep learning model in binary code analysis. Before I start, I want to introduce some application of deep learning model in binary analysis. With the rapid development of deep learning technique those deep learning models are widely used in binary analysis. For example, the assembling model can take a sequence of raw bytes as input and produce its corresponding assembling code. Other models will also do some analysis where the de-assembled assembly code serves as input and the model try to recover high-level program semantics, including but not limited to variable type, function signature, function name, and binary similarities. All those recovered information is of fundamental importance for many critical security applications, including secure and legacy software, malware analysis, and POC development. However, given the importance of binary analysis in cybersecurity, we are concerned about whether those binary analysis models are sufficiently robust against carefully manipulated input binary. Take malware analysis as an example, where a function name prediction model can help to predict the name of a key function in a ransomware. If the model accurately predicts the name as encrypt all the file, it is easy for a malware analyst to understand this function and to determine the input file is a ransomware. However, if the ransomware author is able to modify the code, but retain the functionality of the ransomware, such modification will make the model to predict a wrong name, for example, printf. Then such a misleading information will make the malware analyst confused. He may think this input file is a benign one, which is something we do not want. So in CV and NLP domains, those deep learning models are shown to be vulnerable to adversarial attacks, not only due to the black box nature of those deep learning models. For example, an image classification model, which can typically and accurately classify a cat image. However, the introduction of a small patch, or we call it a trigger, can make the model do something wrong, which means the model may misclassify a cat image as a dog. So here the question is whether such an issue exists in binary code analysis model. To see the evidence, we start with some manual investigation. So here we investigate a state-of-the-art function signature prediction model. Such a model takes a piece of assembly code as input, and it outputs the corresponding function signatures. Please observe that according to the highlight instructions, the value of RDI is equal to the value of RSI. The value of RSI is equal to the value of RDI plus 24 at that program point. So in the next instruction, we replace RDI as RSI minus 24. So we can say that such a change does not change the functionality of the input assembly code. However, such a subtle change indeed makes the model make a wrong prediction. That is, the model misclassifies the second argument as a pointer instead of an integer. With further investigation, we realize the register RSI is the register carrying the value of the second argument according to x86 calling convention. So due to this fact, the compiler tended to generate tons of samples where the second argument is a pointer, and the corresponding assembly code include a dereference instruction of RSI. What does it mean? It means during training, the model is trained on naturally biased dataset, where the model may find a shortcut, that is, as long as the input assembly code contains a dereference instruction of RSI, the model will predict the second argument as a pointer. But we are not so sure whether this is a special case or this is a prevalent issue. So we developed a systematic approach named PELICAN. PELICAN is an adversarial attack method designed for exploit naturally trained binary analysis model. So PELICAN takes a victim model and a small set of clean binary as input. We first leverage a trigger inversion technique to invert a trigger instruction or a set of trigger instructions. Regarding such trigger instructions, as long as the input binary contains such kind of trigger, the model will make a wrong prediction. Then the next step is to inject the trigger into the subject binary. We will guarantee that the program semantics of the subject binary remains the same before and after the trigger injection. In the next slides, we will roughly discuss how we achieve the trigger inversion and the trigger injection. The first stage is trigger inversion. Give a small set of clean binaries. The first step is to insert a random instruction X at a random location in each binary. So please note that this random instruction X is universal, which means it remains the same across different binaries. The next step is to set a universal output as the target prediction that we aim to or we enforce the model to produce. At the last step is a very typical step where we use gradient descent to find the trigger instruction. So as a result, we will get an effective trigger instruction whose effect is independent from the underlying binary and the injection location. We also address a set of challenges in stage 1, including how to ensure the generated instruction follow the assembly syntax. And also we study how to backpropagate gradients through the token embedding lookup table. Details can be found in our paper. And please note that in this stage, we do not preserve the semantic equivalence. That's why we have the second stage, which is trigger injection. So typically, for arbitrary subject binary, we try to inject the inverted trigger into the subject binary without breaking the program semantics. To do this, we derive a block-level program synthesis technique driven by constraint solving. Specifically, given a base block, we will emulate the base block multiple times with randomly initialized input. This is a process what we call randomized micro-execution. The execution result will be used as program state, and we will use those program state to formulate our constraints. Our constraints need to satisfy the following two requirements. The first requirement is that for each micro-execution, the program state change should remain the same for the original and the generated base block. So this is basically the requirement of that we need to retain the program semantics or the concrete program semantics. The second requirement is intuitive, that we try to ensure the generated block contains the trigger instruction or the set of trigger instruction. With all those constraints generated, we use this resolver to generate the target block. We evaluate our technique upon 15 models in 5 different binary analysis tasks. The first column shows the task, the second column shows the model. The third column shows the edit distance, which is the edit distance between the synthesized block and the original block. And the last column shows the attack success rate. We can observe that PELICAN can achieve over 80% ASR for all the models. So here is a question, like whether the result indicates the current design or the architecture of those binary analysis model is not well developed. So I think, or our answer is no. To better understand the situation, we investigated the root cause. Recall that in our previous slides, we show an example where the model overfits on some syntactic feature. Note that due to the nature of compilers, the compilers tend to generate specific code pattern for specific task. So it means the model will be trained on a naturally biased dataset. And the model may mistakenly focus on some syntactic feature, or in our case, the trigger instruction, other than the semantic features. So to see the evidence, we studied the relation between the ASR and the bias label. To measure the bias, we introduced two metrics. The first one is the sample level bias, which is how many target class samples are in the training set. And we also have a feature level bias, which measures the frequency of the target syntactic feature, or we call it trigger instruction, in the target class samples and in the non-target class samples. The result shows that the larger the bias is, the easier the attack can be launched. The results somehow quantitatively support our hypothesis. So due to time constraint, I will skip related work. So it comes to our conclusion. First of all, we observe that the current binary analysis model are not sufficiently robust against carefully designed input binaries. We suspect the root cause is mainly due to the natural bias introduced by the compiler. And we advise the future model development to take care of such kind of bias in case such kind of vulnerability lies in the output binary models. Okay, so that concludes my presentation, and thanks for your time and attention. Now I'm happy to take any questions.